If you're an electronics design engineer, you've probably been asked before to review printed circuit boards, which may come from a variety of sources like junior engineers or OEMs or external third-party consultants. And whilst doing that, there are so many things that can potentially go wrong. So how exactly to perform a good PCB review? And in today's video, I'm going to look specifically at my personal checklist that I employ when I review printed circuit boards, in particular with respect to electromagnetic compatibility and associated issues such as transient voltages and ESD. So let's dive straight into it. Here is the board that I downloaded from the web. This is a millimeter wave radar from Texas Instruments that is based on IWR 6843 chipset. So you can see it here, and it's got 4 receive antennas and 3 transmit antennas. We're not going to review that. I know this part works actually quite well, but there are some issues on this printed circuit board which concern a much lower speed and much more frequency signals. So this is the board we're going to look at today. And if you look closely here, you'll see that there is a statement that says for evaluation only, not FCC approved for resale. And FCC, as you probably know, is a federal commission for communications in the US, and it's an equivalent of a CE mark for radio equipment devices. So there is a good reason why this board is not approved for resale by FCC. Anyway, as a first thing, I would typically look at the block diagram, and if your device doesn't have a block diagram, I highly suggest that you create a block diagram for it. That helps me to understand the general concept of the board, what it does and what the different parts of the IC are in charge of. So we can see we have a PMIC, which is a power management IC here, which provides supply to IWR radar chip. And that is essentially all. There is no microcontroller here per se. There is an embedded integrated microcontroller inside the radar chip, but for that reason you see there is also an EEPROM memory and a QSPI flash, but there is no FPGA or anything like that here. There is an external 60-pin connector that allows you to connect external microcontrollers to it. By the way, this video is not about the schematic review of electronic circuits. For that, you should probably consult a datasheet of the device or try to find other sources if you want to understand, if you're not sure how the circuit is supposed to work. However, I'm going to focus just on the PCB as is without going into too much detail about its individual components. So from the PCB point of view, the first thing we're going to look at is the layer stack manager. And when you open a layer stack manager in Altium Designer, you're going to start seeing things like this. And one of the first things I look into is the distance between planes. So, and the top, for example, copper, and there is a ground below it, and it's separated by 0.1 millimeter. So this is actually a pretty good value. We can also change to mils. So this is equivalent to 4 mil, and that means that if we have components on the top layer, high-speed components, they have, in theory at least, a very adjacent and in a close proximity to them available reference plane, which in this case is indeed labeled as ground. So that gives me confidence that this reference plane is going to work for my IC and provide a good and very short length return current path. So then we can check other layers and see what the distances between them. For example, layer 3 and layer 4 have a 10 mil distance from one layer to the other, so there's not going to be good coupling from one to the other, which is probably a good thing if they are signal layers, and not a very good thing if it's a ground layer. So that sort of thing is very important to check. And then we also gonna look at the impedance profile. So if the board doesn't have an impedance profile, that is already an orange flag to me. So if I open a board that doesn't have anything, it's just blank, there is a possibility that the designer used an external tool to look at the impedance matching. But if that's not the case, then most probably they haven't really thought about it. So that's something to check immediately. So when we look at the impedance profile, here we see we have two types of controlled impedances. This is 50 ohm single-ended and 100 ohm differential. And we can see that actually the deviation from the target is really small. So in fact, if we're using if there are LVDS tracks that require 100 ohm differential impedance on the top layer, they have pretty much a perfect match when the L2 ground layer is used for reference, so as a return plane. And that is a very critical thing to check, because if a board obviously doesn't have a good impedance profile that's matching, then there are some potential EMI issues here. But let's not get into details too much yet. So let's go back to the PCB. And here we can start seeing some differential pairs, like these ones. So these are LVDS indeed, and they do seem to have pretty good return plane below them. So this is the next thing that I start looking at, and here we go. So you straight away see that there is a cutout on the return plane below the IC. So this is, remember, the adjacent plane just below the top layer, and you see there is a cutout here for some reason under the IC. So that itself is not a very good idea, because the currents that flowing through this IC, they may not see equal ground potential due to this broken plane underneath the IC, and that is very often results in a pretty long return path, which means a long loop, and as a result increased EMI profile, so more emissions, because electric field created by magnetic field creates magnetic field and creates electric field, and so on. So the electromagnetic wave with large loops originates in larger areas and propagates at much further distances. So if we want to close our loops as soon as possible, we don't want to have a non-uniform distribution of ground reference planes. So we want a very solid and uniform ground plane just below the IC. And I can see that the designer here had good intention in general, but they decided to split the ground for radar. So to have this, even though it's the same net, which is very funny here, but for analog PLL, they decided to have its own kind of a plane, which is cut by this keep out trace. We can also detect this issue by using the PCB for EMC software, which is an AI-based checker for potential radiated emission issues on the circuit boards, and is entirely Gerber file based and does not use learning, so it doesn't store any data. And it's specifically designed for purposeful debugging, such as this one. So let me show you an example of how we would do that real quick. So first of all, let's open the PCB for EMC website and head to the EMC analysis page and access the tool. So I'm going to skip the login because I already have an account, but you must have a login. And if you don't have, you have to register, then you will have ability to trial this software by yourself. You'll get 2 Gerber file uploads for free. So the first thing you're gonna check is gonna find out the outline of the board. We see that this outline actually matches in this case. Now we're loading the PCB data. Then we can populate the PCB layer stack from Altium Designer, so we see those values here. So this is the most important part, to set the thickness of the dielectric. And for the copper weight, we typically have 1 oz, so it's not really clear from this. So I'm going to assume, oh yes, actually, wait. 1 oz, yeah. We have 1 oz for every copper layer. And interestingly enough, since this is an RF PCB, the first dielectric is RF Rogers R04835, which is a low loss dielectric designed specifically for radio frequency signals, so that at 60 gigahertz it doesn't incur substantial losses, unlike FR4. So that's got a different dielectric constant to the rest of the board material, and it is 3.5. So we're also gonna set that to get accurate results. So we can change the dielectric, and in this case, the rest of them was 4.17, at least according to that PCB layer stack up. Now the actual decay of FR4 can vary from one vendor to another quite significantly, so you have to check exactly with the vendor that your fabrication house uses if you want to have an exact result, of course. So then we click rearrange layers and we can start the assessment. And then after a short while, you're gonna get the result. And as we can see, which kind of confirms our observations, the plane quality on the inner layer 1, which was meant to be the best ground plane, so it's a reference plane for the top layer, is not really good. So we do analytics based on the total coverage area versus the size of the PCB, and when we detect split planes, like we saw in the previous example, then that is a red flag for the analysis tool, and I agree with this assessment. Then we have an excellent quality for the inner layer 6, so we can have a look into that, and in general, this is actually the only return plane of excellent quality that's basically going to act as a reference plane for all layers, in fact. And why is this such a critical problem? Let's now go back to Altium Designer and find this impedance table again. And we see that traces on the top layer and let's look at single-ended traces on the top layer. When they have a reference, bottom reference, as L2 ground, their width should be 8.1 mil, which is a very sensible number, and then the impedance is 50 ohm as the designer intended. However, if the reference plane is not L2 but L7, let's just see what happens. Suddenly, the recommended width for the trace jumps to 95 mil, and for those of you who don't understand those numbers, this now corresponds to 2.4 millimeters, so it's huge. The recommended trace to achieve 50 ohm impedance has jumped from being a tiny normal size PCB trace to absolutely huge. So that means that if I had my trace as before at 8.1 mil, let's just insert that value. The impedance on that trace is 134 ohm. So it jumped, it tripled in value almost. So this is the critical issue. And when the plane cannot be used as a reference because it's broken, the trace is going to find the nearest suitable return plane, which in this case is going to be layer 7. So we can also see that from the PCB stack, because here is a uniform ground plane, as we basically predicted from looking in the PCB for EMC software. So let's carry on, and we look at a few other things. So for example, we've done our analysis now. We can identify some of the traces. So here are some of the differential nets, which in this case are LVDS pairs. And actually the impedance seems to be relatively spot on. So when it's referenced against the adjacent plane on layer 1, which in this case it's okay because the cutout actually just happens to be here. So if the cutout crossed those traces, the impedance value would also jump, but in this case it's not the problem for LVDS traces, but it is the problem for the IC itself. So we can look at other traces on other layers and analyze the impedance there. So in this case, there are a bunch of traces here which actually don't look like differential pairs to me. For most of the part, they look like single-ended, and in this case, the single-ended impedance again seems to be spot on. And what else we can do? We can look at potential crosstalk issues, and this is another potential problematic area with this PCB, because if I select these two traces, for example, which you can see are very adjacent to each other, there is a very high probability of crosstalk. And this is something I would also immediately look into when reviewing printed circuit boards, is whether or not those traces have been spaced appropriately, especially if we're talking about clocks. So we can look at the PCB, find those traces. So let me go to the single layer view mode. Yeah, I believe these are the traces we looked at. So in this case, those are just GPIOs, but not all of them. So you see, this is actually a clock signal. It's a clock output from the power management IC. And you can see that this trace has a very high crosstalk potential to couple into radar DP5, which is a GPIO. Now, it entirely depends how you're gonna use that trace. If you're gonna use another clock on this trace, there is a very high probability of it beating against one another and neither of them working. So that's the next thing to look into, the right way to route clock traces like this. is to put a ground trace in between them. Now, whether or not I would be able to do that is a different issue, but ideally we would want to move that as much as possible like this, such that we can insert a trace in between, and like this. So now those traces are going to be significantly separated on the printed circuit board, and we can see that if we report the plane. So that's one way to overcome this issue, and when you have clock traces like this, that would be the right way to trace them. Then we also have a few differential pairs on the inner layer 5, just above the only excellent plane that we have on this PCB, and we get these traces here, so we can analyze the ground, which in this case you see the ground plane for traces is really good, and that's basically what we're talking about. But for one of these traces, it's not as good as for others. I wonder why. So this is another thing that you get to highlight when you do this analysis, and we can then have a look at what can we possibly do better in terms of routing this signal. So let's take a look. So this is the pair. We see that it's not exactly clear what differential pair that is. So if we look at the propagation path, it does tend to have a rather good return plane. So, but yes, there is a bit of proximity to those wires. So that's possibly what's triggered the software to say that one of the plane, most probably is this area here. One of the traces just doesn't have a very good return path in this particular area. It's more so one trace than the other. It's not both of them. So it's a relatively minor issue, and again, you can easily fix that just by slightly rerouting these traces to make them more away from this edge, basically wires. Or you could remove one of those wires. In this case, it's just a 5 volt. So it's probably not necessary, and that alone is going to increase the ground plane quality below those traces. We can also do differential pair crosstalk analysis using this tool. So let's pick a couple of traces. For example, let's pick a couple of differential pairs, let's say. So 4 traces in total, and we see that they are quite close, but also separated. So I'm interested to see the result here. We still consider these as high crosstalk because this space is very small. It's just 1 width of a single single-ended trace. So depending on what those differential pairs are, you may experience some coupling from one pair into another, and if they especially if they have significant voltage differences. Then the next important thing to check when you do a PCB design review is the power supply, of course. So in this case, I already mentioned there is a PMIC, the power management IC on this board. So let's have a look at that. Let's find it. You can usually find the PMIC by the abundance of capacitors around it. So you see here we have a few capacitors of various values and inductors. So that is in fact the PMIC LP87524. So let's have a look at the layout if there's anything we want to change here. So first of all, I also check the ground plane quality below the PMIC. In this case, it looks good to me. So it's a solid. There's no splits in the ground plane. It's quite solid. So there's no issue. Secondly, I look at the decoupling capacitors. So in this case, they're here. C74, C72. The distance from the capacitor to trace is just 8 mil. So that's pretty short. That's really good. As a rule, the length of the trace from the pin or power input pin to decoupling capacitor should not be more than 2 millimeters, including the PCB thickness, and that corresponds to approximately 78 mils, if you're interested. So that is because the pin may require a high speed current when it's switching, when it's changing the state from 0 to 1, and if the capacitor is placed too far away from it, it's not going to be able to supply this demand to this current to satisfy the IC, which results in the IC being drained. So the draining this current will result in increased noise from the IC. And that's why it's very important to provide very closely placed decoupling capacitor for each power input pin. So I would typically place one capacitor per pin for every IC, and especially for microcontrollers, PMICs and such. It's really critical. So in this design, we can see there's no major issues actually associated with that, and we can only check the value of the capacitor to be effective at high frequencies. It shouldn't be high. In this case, it's 10 microfarad. So this is something that maybe I would tune. I would have 100 nano, such close proximity to the power input, and then maybe another bulk capacitor with a little bit more farther away. So that's the only minor kind of comment I can make here. But again, this IC actually is not that fast. I believe it's switching around 1.5 megahertz or something like this. So it's not as fast as an FPGA or something. So this is not going to be as critical. Then for ground of this capacitor, we see that the designer did an excellent job here by stitching this return path with loads of wires. The only, again, minor detail is it would probably help to have a wire here as well. Let's see if that's possible, like here, between the pin and capacitors. So that would help to return the current, to provide a shorter reference for return path to the ground plane from the pin, directly from the pin into the plane. Whereas in this case, without this wire, it has to flow via capacitors first, so this length is a little bit longer. Again, no big deal, but it is a little bit long now. It's 2.7 millimeters, so it's slightly exceeding the desired distance of 2 millimeters, and that is a reminder including the board thickness. So if you place the capacitor on the opposite side of the board, you have to take into account that the PCB thickness is 1.6 millimeter, so you shouldn't space it more than 0.4 millimeters away from the wire. So overall, it seems to be a pretty good job here. I don't have more comments on the PMIC. We can of course also check that those inductors have been appropriately selected and have sufficient current rating, which in this case it is 4.5 amp. So, and There are plenty of capacitors there on the output, so it seems that the designers have put in quite a lot of attention into this side of the printed circuit board layout. There is even a snubber network on the output to basically filter it and remove the noise. I mean, it seems that those values have been carefully calculated, although you would have to look through the datasheet to find out the exact formula. Whilst we're looking at schematics, we also could look at the memory. So typically memory is quite important, and I see this is something that I do as well. I place series resistors on SPI, and this is QSPI. Nevertheless, it's the same. So those resistors help to reduce the ringing on the SPI single-ended transmission lines. So basically it smooths the clock edges overall, and you want to place those resistors as close to the IC. So let's see if the designer's done that. And yes, they have. So these resistors are pretty close. This is a very funny trace. So it looks like it's also been length matched, which is quite good for the QSPI to length match, but typically is not necessarily. So I sometimes see it, sometimes don't. And that's often done on the longest trace. So on the longest trace and the routing, so which is probably this one, then the designer had to length match all the others to make them exactly the same. And that is to make sure that the IC, basically all the data pins of the memory chip have the same length. And it's a good practice. It's not very necessary on low speed QSPIs, but it might be necessary here actually. I'm not sure which IC is that. It could be quite high speed. In fact, you never know with them anymore. So there we can also check the decoupling capacitor placement. Again, it looks pretty close. So meets the requirements. And what more we can ask for? There's also a good connection of the ground pad to the plane. The plane is not interrupted. So this IC is also in a pretty good order. Finally, we can look at the schematics for the IC itself and notice that the designer did not use differential net identifiers here. It is specified as 100 ohm differential traces, but they did not use the conventional differential pair identifier such as this one, and that is something I would recommend doing, so that you can set up your rules to make sure that the differential trace impedance is checked as part of your design rule checker. We can also see that the designer did not put series resistors on the radar SPI, which is going, I believe, to an external connector. And yes, it's going here. And indeed, there are no resistors in series on these traces, which is not ideal. Especially since those traces are leaving the board and you don't know how long they're gonna be. It's always a good idea when you connect traces to an external connector to put at least a small value series resistor on a trace. Finally, there is a crystal oscillator Y1, and that is a pretty simple circuit which has a ground connection from two of its pins. So we can find that, and I believe it's here. So this is exactly where the ground cutout is that I've been talking about. In general, it's not a big problem, but the problem is that this cutout is maintained under the IC as well. And I believe this is the reason why this particular board doesn't pass FCC testing, and it creates a harmonic at around 28 gigahertz. Which is a second order harmonic of its 14 gigahertz PLL clock. You can read more about it on the TI website, but there is no proposed solution by the TI. And here is my proposed solution: unify those ground planes. Anyway, as the last thing, we can also check the connections from this board to the external world, so to the outside world. And I already mentioned that it's a good idea to put series resistors on the traces that leave the board. But also, what else we must consider? And of course, it is electrostatic discharge. If it's applied to a cable or it's applied to the port, like external I/O, it's likely to destroy the device unless it has adequate level of protection through transient voltage suppressor diodes. So let's have a look at that and see if the designer has put those in place. So when we look at the PCB, we can start to understand where is the ESD likely to propagate here. And immediately we notice this connector here, J5, which looks like a USB, micro USB socket. And this is one of the primarily sources of potential electrostatic discharge that may come via the cable on the pins or the shield of that connector. So let's find that. Okay. And as I suspected, because it's an evaluation board, it doesn't have any transient voltage suppressors here. So if I were to apply a 4 kilovolt ESD onto this port as per the IEC 61000-4-2 standard for commercial testing of office and home equipment, then that's very likely to blow up an integrated circuit on this board, which is most probably going to be the radar IC where these USB signals are connected to. So, of course, these are not really... actually, it's not connected directly, is it? It's connected via UART. So this is the IC is going to blow up. It's a USB to UART bridge. So most probably this IC was not designed to withstand electrostatic discharge. We can double check that, but I'm pretty sure that's the case. So we can open the data sheet and we can just search for ESD. Yeah, and the note says the ESD protection should be added in the design, and it even recommends a specific part number or equivalent. So this is what I'm talking about, and otherwise the IC is not going to withstand an electrostatic discharge. So yeah, this is definitely going to be a problem on this board. And whilst on it, we can look at other sources of potential ESD. We can see their pins are accessible here, J4 and J3. I am not sure what's gonna be likely to be connected to those pins, but it's very easy to also discharge ESD if you touch it accidentally or intentionally into those pins. So if this were my board design, I would also put transient voltage suppressors here if they were to stick out like they do here. Other than that, there are not many potential sources. The antennas are of course not going to be touched. There's not connectors, they are actual antennas, so no one's going to touch that, so there's no issue here. And yes, I believe that's about it. So that is my top 5 list, if you like, of the things that I would like to check for electromagnetic compatibility of printed circuit boards. And I hope you enjoyed watching this video, and you also saw the example using the PCB for EMC software that we developed. Feel free to evaluate it and see how it can be used for your purposes. One thing I did forget to mention is that if we go back to the tool, we can also generate a very nice report at the end of our session. So like this. And this report is just going to show you everything that we've seen, that there may be potential issues with ground planes here, but on the layer 5 we have very good quality, and we have a crosstalk analysis that we perform. So it's just a summary of what we've just been doing and evaluating potential problematic issues concerning radiated emissions performance. At the moment, the tool does not do much in terms of ESD analysis or decoupling capacitor placement, but it is something I would like to introduce in future revisions. So please be in touch, review the tool as it is, and let me know your feedback, and we'll try to work together to make it better. I hope you enjoyed this video and it gave you some valuable insights into how to analyze printed circuit boards and troubleshoot them on the first sight. So finding out potential issues concerning electromagnetic compatibility. And yes, don't be a stranger, be in touch, let me know what you think about the PCB for EMC tool, and I'll see you in the next video very soon.